Okay, so this video is going to go through integrating exponential functions, and then also log or a function that will result in the natural log as its antiderivative. So I'm hoping that like the fact that exponential functions are their own derivative, like we saw that a few chapters ago, like the derivative of e to the x is itself. Therefore, the integral of e to the x will also be itself, right? It's almost like it's an identity an identity function. Just don't forget the plus c. And then, if you remember the derivative when you had like a to the x, like 2 chapters ago. So the derivative of a to the x, remember, of a to the x, you still got a to the x, but you had to multiply by the natural log of the base, right? The natural log of a. And so when we're doing the antiderivative, we have to do the exact opposite. So we divide by the natural log of that base. So those two aren't too bad, but most likely you're going to need a u substitution. It's not going to just be an e to the x or an a to the x, but the good news is that that exponent often makes it, a perfect candidate for the u, because if you can look at that function and reduce it to just a u, then it's its own antiderivative, which is nice. So let's let u equal x squared. That's the exponent. Its derivative is 2x dx. We need a 4, so we're going to multiply both sides by 2. So 2 du equals 4x dx. So now my 4x and dx can be replaced with 2 du. And it just becomes e to the u. And, I always say that this is sort of like the anticlimactic antiderivative, because you're done. Like, what's the antiderivative of 2e to the u? Itself. And then just don't forget your plus c. So there's like really no work, right? You're just, here it is, you're done. And then just go back and put u. So 2e to the x squared plus c. And, I stressed this in the last couple of videos, and I'll stress it again. It's so much easier to take a derivative. So much easier to check your work. Like real quick, you could say, that's just, so that's 2e to the x squared times chain rule 2x. And that simplifies perfectly. So much easier to do a derivative. Okay, next one. Same idea, except for now we've got this extra step here because our base is 2. We'll go ahead and say let's let u equal the exponent. That's always a good bet for your u substitution. Du would be 3x squared dx. And then we only have an x squared dx, so we need a 1/3 du is equal to x squared dx. And then we do the integral. So it's the integral of 1/3 of 2 to the u du. And still anticlimactic in a way, just don't forget to divide out your base. So it's 1/3 2 to the u divide by natural log of 2 plus c. And obviously, I wouldn't clean that up because the 3 can go down in the denominator. So we get 1/3 natural log of 2. Although I like that 2 to the u. So let's go ahead and put that also in the numerator. And then remind ourselves that u was equal to x cubed. So 2 to the x cubed plus c. And, a lot of times I feel that the answers are very cumbersome or clunky, not aesthetically pleasing. So that's fine. If you realize that 3 could come up with an exponent and call it natural log of 8, because that's what 2 to the 3rd power is, that's fine. However you want to do that. And then this one here, I like this one. It's a good reminder that even when you have a linear function, technically that's still u substitution. So, I don't have anything outside here, and that's okay other than 1 dx. But I still need a u substitution to account for that transformation. So let's let u equal 1 minus 2x. So that means du is negative 2 dx. And again, we just have a dx. So negative 1/2 du is equal to dx. So now we're going to integrate negative 1/2, and there's our du. And it's just e to the u. And if I change my bounds, then I don't ever have to go back to x again. So 0, if I do 1 minus 2 times 0, so 1, and 1. So 1 minus 2 is negative 1. So now I don't have to worry about my, my x's again. And it's its own antiderivative. And then instead of a plus c, we say when u goes from 1 to negative 1. So then it's, it's a little bit, it has a feeling of backwardsness because I have a smaller number on top than the bottom, but I still have to go in order. So it's f of negative 1 minus f of 1. So it's negative 1/2 e to the negative 1 minus negative 1/2 e to the 1. And those obviously become a plus. E to the negative 1, if you want to write it as an exponent that has a positive value, you could do that. So like it's like negative 1 over 2e plus 1/2 e. If you want to factor out the 1/2, you could do that as well. I mean, it's really however you want. And if you want to put that e first, like this e right here, so you can say like it's e minus 1 over e, that's fine too. Okay, and then another practice here with bounds. So this one, oh, that's weird. Like 5 is almost exactly like 4 or 3. So again, if you want to fast forward and just do these, that's fine. There's really no substitution here. It's its own antiderivative. So it's it's 2 to the x divided by natural log of 2 when evaluated from 1 to 4. So that's kind of a nice little gift. 2 to the 4th power is 16 over natural log of 2 minus 2 to the 1st power over natural log of 2. Common denominator, so 14 divided by natural log of 2. Again, kind of clunky, kind of clumsy of an answer, but that's what it is. Okay, and then, like our next example, another u substitution. The only difference, instead of like e as our base, it's 3. That's okay. So let's let u equal 2x plus 1. The derivative is 2 dx. We're off by a factor of 1/2. So now this becomes the integral of 1/2 du. It's 3 to the u. And we can go ahead and transform our bounds. If I put 0 in for x, times 2 plus 1 is 1. If I put 1 in for x, times 2 plus 1 is 3. And then we do everything we could just leave in terms of u. So 1/2 3 to the u divided by natural log of 3, because that's our base when divided by 1, or sorry, when divided from 1 to 3. So then we could say that's 1 over 2 natural log of 3. I'm just kind of putting those two together, times 3 to the 3rd minus 1 over 2 natural log of 3, times 3 to the 1st. And then I know 3 to the 3rd is 27. 3 to the 1st is 3, so like 27 minus 3 would be 24. So I mean, they're already common denominators, right? So it'd be 24 over 2 natural log of 3. Or if you wanted to move that 2 in front, as an exponent, you could, and you could call it 24 divided by natural log of 9. So, the whole, like the goal, or I guess the takeaway is that e to the x is its own antiderivative, and then any other exponential function is its own antiderivative. Just remember to divide out the natural log. Okay, so I think it's a good spot to end this video, and then I'll make one more for the for the next column.